We're going to continue on with normalization topic. So let's talk about forms. The first one is boycott normal forms, short for BCNF. Okay, let's assume that we have R that has A, B, C, D, G, and H. Okay, so we have some dependencies. Alpha determines beta. Okay, so for each of the dependencies of R, okay, so at least one of these two have to be true. So either this is trivial, meaning the left-hand side is a subset of the right-hand side is a subset of the left-hand side, or the left-hand side is a superkey, meaning with the left-hand side, you're able to get everything in R, meaning A, B, C, D, G, and H. So here's an example in that, which is in department. Okay, so we have ID, name, salary, department name, building, and budget. Okay, and then these are going to be our dependencies. Okay, we have department name determines the building and the budget. For each department, there's only one main building and there's one budget. Okay, so let's see if one of these are true. So let's first check the first condition where this is trivial, meaning the right-hand side is a subset of left-hand side. So I'm not seeing building or budget on this side, so this is definitely not true. So let's see if the second one is true. So the left-hand side is a superkey for R. So the left-hand side is department name. So this I said is the closure, right? So we're going to take the closure of department name and we are able to get department name because that's trivial. What else can I get? So with that, I'm also able to get the building and the budget. Building and budget, and there's really nothing else, right? So with this, I'm able to get department name, building, and budget, but not ID, name, or salary, so which is not the whole relation, right? So this is also not true. So this one violates the rule for BSCNF. Okay, so we need to decompose this particular relation into two subsets. So we will decompose it into instructor and department because it broke the law. It violated the rule for BCNF because none of these two were true for this functional dependence. Okay, so we will call one instructor and one department. So there's just pretty much a formula that you follow to do this decomposition. Okay, so R1 is going to be the left-hand side and the right-hand side of the functional dependency that was breaking the law, which was this one, right? This one, department name determines building and budget. So the left-hand side of this is department name. The right-hand side is building and budget. So R1 is going to have, or in our case, the instructor will have, actually it's going to be department has department name, building, and budget. Okay, and then R2 is going to be the whole entire relation R, and then we're going to be subtracting beta minus alpha. Okay, so R1 is pretty much the left and right hand side. Okay, so it was department name, building, and budget for R1. R2 is going to be this whole thing, and then we're going to be subtracting whatever was on the right hand side. The right hand side had building and budget. Okay, so we're going to take the whole relation R and then we're going to cross out building and budget. And we are left with ID, name, salary, and department name. Okay, so since alpha is department name and beta is building and budget, R1 is left and right, and R2 is this whole thing, and then we're subtracting beta, which is building and budget, and this is what we're left with. So you can see that R1 contains information on the other department, and R2 has information on the actual instructor. Okay, so this is how you decompose it. So let's take a look at another example. We have R that has A, B, and C. It has two functional dependencies. Okay, so we talked about this in the previous lecture, right? So since R1 and R2 have B in common, and B gives you B and C, which is R2, this is lossless, and it is dependency preserving because A determines B is in here, B determines C is in R2. Okay, so ideally we want to decompose something in a way that it is lossless as well as dependency preserved. Here's another example. We have department advisor table, which has the student ID that's being advised and the instructor ID. So this instructor is doing the advising on the student and the department name. Okay, so we have two functional dependencies. So it's, a lot of times this is given to you, but just, from common sense and just knowing the facts, you are able to come up with some of these dependencies. So if you know the instructor's ID, you know the department name because each instructor belongs to one department. If they are in multiple departments, they will, at least have a main one and secondary one. Yes. So for each instructor, there's going to be exactly one department that are associated with the instructor. Here's another one. So if you know the student's ID and the department they belong to, you can, so there's only going to be one instructor that will be assigned to this particular student and not more than one. Okay, so these will be our dependencies. So we want to check to see if this is dependency preserving. It may not always be. Okay, so department advisor is not in BCNF. Why? Because we need to check each one of these functional dependencies. Let's first check the first one. Instructor ID gives you a department name. Okay, so is this a subset of left hand side? No, department name does not appear on the left hand side, so the first one is not true. Is the left hand side a super key for department advisor? Let's see. So with IID, I can get IID. That's trivial. And using this one, I'm also able to get department name. So with IID, I can get IID and department name. Okay, but I cannot get SID, right? So IID is not a super key for this particular relation. So this one does break the rule. Okay, so using the rule, we are able to decompose it. And what about this one? So we have SID and department name determines IID. So is IID a subset of the left-hand side? No, IID does not exist on here, so the first one's not true. The second condition is the left-hand side a super key for R. Let's see. So with the SID and department name, you can get itself, which is SID and department name. And with that, I'm also able to get IID. Okay, so which is the whole relation department advisor, right? So the left-hand side indeed is a super key. So this condition, this functional dependency, does not break the rule, but this one does. Okay, so that means that we have to decompose department advisor further, and we do that using the formula that was given to you, but we do that using the dependency that was breaking the law. So this one was okay, this one was not. So we're going to use this. So it would be one. So R1 would be the left and right hand side, which will give you IID and department name. And R2 is going to be the whole relation R, and then you're going to subtract the left hand side. Okay, so here, the right hand side. Okay, so we're going to just plug it in, R minus right. Okay, so right hand side, in here we have IID. So if I take this whole thing and cross out the IID, we are left with SID and the department. Okay, so that was BCNF. BCNF can be hard to achieve at times, and with BCNF, dependency preserving is not always guaranteed. Sometimes in the process of decomposing it, we might lose one or more dependencies, which is not ideal. So because of that, we sometimes use another form called third normal form, short for 3NF. Okay, so this is very similar to BCNF. We have the first conditions that are exactly the same as BCNF, but we have another condition where if both of these are not true, but if this is true, it's still going to be in 3NF. So this third condition says each attribute A in beta minus alpha is contained in a candidate key for R. So each attribute in beta minus alpha, a lot of case, which is just going to be beta. Okay, so if that is contained in one of the candidate keys, then that one does not break the rule. Okay, so let's take a look at this example. We have department advisor, the same example we were talking about. And then this one has two candidate keys. We have SID and department name, because with that, we can get IID, which is the whole relation. Okay, SID and IID. So we have IID, which gives us IID and department name. along with that is SID, that's the whole relation. So these are going to be our two candidate keys. So IID determines the department name. This one did break the rule for BCNF because this was not a subset of the lesson site. IID alone was not a super key. So we have this third condition where each attribute A in beta minus alpha, which would just be department name, is a subset of a candidate key. We have two candidate keys here. So is department name part of any of these? Not in here. It is part of this particular candidate key. This one, in fact, does not break the rule for 3NF, so it is in 3NF. This one, this works because SID and department name is a super key because with this, you are able to get the whole relation. Okay, so both of these don't break the rule for 3NF, and it is already in 3NF right now. Okay. So there are some redundancy in 3NF. So here, this example has J, K, and L in R. We have two functional dependencies. JK determines L, A determines K. Okay, so here is an instance table where we have some values in here. So what is wrong with this table? Okay, so I'm looking at J1, L1, K1, J2, L1, K1, J3, L1, K1. So I'm seeing, a repetition of, L1, K1, L1, K1, L1, K1, and three different rows. Okay, so kind of a repetition, right? And then here, for L2 and K2, we don't have a value for J, it's using a null value. Okay, so with 3NF, you do have some issues like this where you have repetition of information like this, or sometimes you're having to use null values. Okay, so there's pros and cons for using, BCNF and 3NF. So let's compare the difference between BCNF and 3NF. So advantages to using 3NF is it's always going to be lossless and dependency preserving, as in BCNF, this is not always a guarantee that it's going to be dependency preserving. Okay, so, but what about disadvantages to 3NF? So like the example I just talked about, sometimes there's a repetition of information and sometimes you have to use null values when it's missing some data. So we say that R is in a good form when it is dependency preserving and it's in lossless form. So when you decompose it, we want to be lossless and we will prefer to not lose any of the functional dependency. Okay, so how good is BCNF? BCNF, again, is harder to reach. How good is it? Let's see. So there are database schemas in BCNF that do not seem to be sufficiently normalized. We have instructor information, which has the instructor's ID, the instructor's child's name, as well as their phone number. Okay, so this is what you see in the table. There is, so the ID here is 99999. So we're dealing with the same instructor here. And for the child's name, we have David in 2 rows, William in 2 rows. Here we have phone numbers. We have 512-555-1234, which I see in 2 different rows. And I have another one that ending in 4321, which I see in 2 different rows. So this is not really ideal. You have repetition of information in this case, right? So there are no non-trivial functional dependencies, and therefore this is in BCNF. So what happens if I were to try to add another phone number or maybe try to add another child to this one? Okay, so let's say I had this instructor had a child named Natalie. Okay, so how many rows of data would they have to add Natalie as a child? Is it just 1 row or 2? They would have to add 2 because this instructor happens to have 2 phone numbers, right? So what if they had another phone number, 3 phone numbers? Then it's just gonna have, 3 rows of data for each child, which is not really ideal. So BCNF is not perfect. There's insertion anomalies, such as when you want to add another phone number, add another child, you're having to add extra rows of data, which is not good. Okay, so there are higher normal forms, such as 4NF, which we will not cover in this case, but yes, in this form, you are able to decompose it further from BC enough to far enough to kind of avoid this issue where one table is dealing with instructor's child only and another table is dealing with the instructor's only phone numbers. And that way, when you're trying to add another child, you just need to add one more row, and same thing with the phone. So we talked about closure a little bit, but I never formally mentioned this. So here is what we call a closure of a set of functional dependencies. So if we have A determines B and B determines C, we can infer that A determines C. So if you know A, you know B. And if you know B, you know C. So that means if you know A, you know C. So there are different names for these axioms. Okay, so A determines A, B determines B. These are all trivial because obviously these are the same values. Same thing, AB determines A. Since A is a subset of the left-hand side, it's reflexive. So we call this reflexive. Okay, so the set of all of these dependencies that are logically implied okay, by F is called closure of F. So the closure notation here is a little plus sign after the actual F, which is the functional dependencies. So there are a total of 6 axioms. 3 are the main ones, and using the 3, you're able to come up with the other 3, but there are names for that. So the first one is if beta is a subset of alpha, then alpha determines beta. So for example, will be, if A is a subset of AB, which is true, right? Then AB determines A. Same thing. If you know AB, you know B. So that's what we call reflexive rule. Okay, so make sure you know these and you also know the name of each axiom. So augmentation is you are able to add an attribute to either side. So we have alpha determines beta. So this means that we can add gamma on both sides and it still be true. So if A determines B, then AC determines BC. You can also do another one saying if A determines B, ACD determines BCD. Okay, so you're able to add the same thing on both sides. Okay, so it's going to be augmentation. Transitivity rule, which we already dealt with, was A, B determines B, and B, C, B determines C, then you can infer that A also determines C. So this is called transitivity. These rules are sound and complete, and these are proven. Okay, so you will have to use some of these to come up with the closure of it. So let's take a look at this example here. We have relation R, which has A, B, C, G, H, and I. And we have a lot of functional dependencies. We have A determines B, A determines C, CG determines H, CG determines I, B determines H. Okay, so other than these, what others are implied using this? Let's see. So these are some members, okay? So since I can combine A determines B and B determines H, I can infer A determines H, right? Using these two. And I believe that the axiom was called transitivity. So whenever you do these, make sure you mention the name of the axiom. Okay, so using transitivity, we are able to come up with this. Okay, we have AG determines I and AG determines H. So this is by augmenting G to A determines C. So we can add G and G here, right? AG determines CG. Okay, so we have that, and then we have CG determines H. CG determines I, which we have here. So using this, I'm able to say AG determines I. Same thing with the H. AG determines H. Okay, we have another one here saying CG determines HI. So here I'm able to combine these two into one. Okay, so CG determines H and I. Okay, so HI. Okay, so these are the rest of the rules. There's union, decomposition, and pseudo-transitivity. Okay, so let's take a look. So we have alpha determines beta holds and alpha determines gamma hold, and we're able to kind of combine and merge the right hand side of these two and say alpha determines beta and gamma. So here, if A determines B and A determines C, we combine it and say A determines B, C. Okay, so that's a union rule. Decomposition is just the opposite. So here A determines B, C, then we can say A determines B and A determines C. That's pretty much the opposite of union rule. Okay, so that was decomposition. Pseudo-transitivity says A determines B, so we can add C to both sides and get AC determines BC, right? And if we have another rule saying BC determines D, then we can infer AC determines D. Okay? So that is transitivity rule, and so using pseudo-transitivity. So these were the three that I mentioned in the previous page. So together, these six axioms, we call them Armstrong's axioms. Okay, so these will come in very handy whenever you are trying to get the closure of F. Okay, so let's see. So here is an exercise. We have R, which has A, B, C, D, E. R1 has A, B, C. R2 has A, D, E. We want to see if this is lossy or lossless. So these are going to be our functional dependencies. Let's first see if any of these have anything in common. So R1 has A, B, C. R2 has A, D, E. So they both have A in common. So what is the closure of A? So with A, what can you get? So with A, you can get A. That's trivial. With A, you're also able to get BC. And now that you know BC, if you know B, you can get D, right? And since you know C and D, you're also able to get E. So actually with A, you're able to get the whole relation R. So the union between R1 and R2 gives you R1 and R2. So the closure of A gives you the whole thing, which could be R1 or R2. So this is in fact a lossless decomposition. Okay, let's see if this was also dependency preserving. So A determines BC. We were to preserve that using R1. CD determines E. No, that one was lost. So that was not preserved. B determines D, also lost. What about E determines A? We actually have that in R2. So we actually lost these two, meaning it is not a dependency preserving decomposition. Okay, here is another one. So suppose we have a schema R, which has A, B, C, D. It has two dependencies. A determines B and B determines C. So what else can we infer using this? So it only has two dependencies, but there's actually a lot more. Some trivial ones, some using, the axioms that we talked about. So try to come up with, as many as possible. So just do your best. Take about 5 minutes to, try to write down as many as possible, and then click play. So here we have some trivial ones, which is, A determines A, B determines B, C determines C, and so on. Those are all the trivial ones. And these two are given to us in F. Okay, so given in F, and then combining these two, we're also able to infer A determines C, and that's using transitivity. So like you say here, make sure you give a reason at the end of each one to kind of justify it. We also have reflexive rules where if the right-hand side is a subset of the left-hand side, then this is true, right? So AB determines A, AB determines B. Okay? AC determines A, AC determines C. So all of those are given here, and this is using reflexive rule. Okay, we also have AB determines C, ABD determines C, AD determines C. Okay, so since A determines C is true, anything here, B, BD, anything else is all trivial. Or this is extraneous, so you actually don't need those, but they're there. Okay, here I have AC determines B, AD determines B. So since A determines B is true, C and D are extraneous. Okay, so we have quite a few here. Here is another one. So using this, what are some other dependencies that we are able to infer using Armstrong's axiom? So let's take a few minutes and see if we can come up with a few. Okay, maybe you can go back to the slide where it has all the 6 axioms and see, which one you can apply to this one. Okay, let's go over it. Here, combining E determines A and A determines BC, by transitivity, we can say E determines BC. Okay, and I did indicate here that by using transitivity for this one and this one, we were able to infer this. Okay, so makes this part's important, how you were able to get this. Okay, we also have A determines CD using pseudo-transitivity. I think this one tends to be the most confusing one for people. It just takes getting used to. So using A determines BC and then B determines D, we're able to infer A determines CD. Okay, if you're not really sure how that worked, you can add C here and here, right? And this implies that BC determines CD, right? So using transitivity between the two, we're able to get A determines CD. Okay, so that's using this one. The last one we're able to infer is using these two. CD determines E, E determines A, so that implies that CD determines A using transitivity. Okay, so there could be more, but these are just